Hello buddy, today I will demonstrate how our project works. uh, you can see that there are some input ports and there are some output ports, and you can see that this is a hierarchical block. This block labeled as signal generation block. Now it includes the two signal, that is input signal and a reference signal. That input signal and reference signal is input of next hierarchy block, that is multipliers. As we can see that in our block diagram, this is our input signal. uh, First this one is our input signal, and then we have a reference signal here. So we can see that the input signal is going towards the multiplier here. This is our multiplier cause and this is multiplier sign, and then it is passing through FIR compiler, and then magnitude is calculated at the output. So if we see that we have a valid signal, whenever the valid signal is 1, then only the input and reference signal will be generated on the output of signal generation block. We can see that there are two other inputs, phase input signal and a phase reference signal. The phase input signal is the value that is calculated from the formula which I have given you in the readme file during the TeamViewer meeting. That we will calculate that value which will be used for our signal generation. For example, for signal of for input signal, for input signal, we have used the frequency of we have used the frequency of let me tell you, this is our reference signal that is generated at 1 kilohertz, and these are our reference signal that is generated at 2 kilohertz, 5 kilohertz, and 10 kilohertz. So first of all, this is the clock that is 200 megahertz, and that is downscaled to 5 megahertz. You can see that this is a 5 megahertz. Let us open the block. We can see that this is the block, and this is our output clock signal that is 5 megahertz. Okay, that is our 5 megahertz output clock. uh, let us go inside this signal generation block. We can see that this is our phase reference signal that is the input towards this DDS, and this is our phase input signal that is input towards this DDS block, and there is a valid signal that is connected to both of these, and a clock signal that is connected to both of these. And we can see that the output of our reference DDS is split into two, that is sine and cosine, and this is our input signal that is used as a sine wave. When we open this, we can see that the input frequency of the clock is 5 megahertz, and a phase width of 16 is used, and output width is 16. In the implementation, we can see that the input signal is only sinusoidal. Only the reference signal is divided into sine and cosine. We can select sine and cosine from here. Similarly, there is a phase angle increment value. Let me tell you about the calculation of this. Remember this value. If we see that in additional summary, we can see that this is 0.00198, means it's about 2 kilohertz. That signal is about 2 kilohertz frequency. That is about 2 kilohertz frequency. Let us calculate this phase and angle increment value. That how we get this value for exactly 2 kilohertz wave. For this we need a calculator. We can see that we want 2 kilohertz frequency, so we calculate here 2000 multiplied by the phase width is 16 bit, and we know that 2 raised to power 16 is equal to 65536. So we multiply with that and divide it with our input frequency, that is 5 megahertz. So we will get a value of 26. When we convert this value from 26 into from decimal to hex, we can see that from 26 we will get this value 00011010, and you can see that this is 00011010, and this frequency will corresponds to 2 kilohertz. Okay, uh, let me calculate the value for frequency of 1 kilohertz. We will go towards the calculator. We will write 1000 multiplied by the phase width 65536, and divide this value with the 5 megahertz and we will get the value of 13. When we convert this 13 from decimal to binary, we will get 1101. When I put 1101 here, it will give us 1 kilohertz. Now you can see that 0009, that is approximately equal to 001 megahertz, that will be equal to 1 kilohertz. Okay, so you can see that in reference DDS, the phase angle increment is 1101 and we will getting a frequency output of 1 kilohertz. Similarly, you can see that we have selected sine and cosine here. So this represents that the higher 16-bit data or MSBs are known as sine and LSBs are known as cosine signal. So we add a split block here and we can see that from 32 down 15 there is a higher most bits that is known as MSBs that will be considered as cosine wave and sorry, those were the LSBs and these are the MSBs 31 down 16 that are 16 bits. So these signal will generate a sine and cosine wave that is known as reference signal. Then the reference signal is about 1 kilohertz and this input signal this is generated of about 2 kilohertz. We can see that in the simulation file we have different configuration for which we get the output of 2 kilohertz, 5 kilohertz, 10 kilohertz, 1.5 kilohertz. We will discuss about that. So let us open the multiplier block. We can see that there are two inputs B and B1. These B and B1 are the sine and cosine signal and this is our input signal. We can see that this is our input signal that is multiplied by a reference. That reference is basically our cos and this is our sine. You have drawn the wrong connection with this diagram. These two pins are this pin is connected with this one and this pin will be connected to with this one and that is our multiplier. So we can see that here is our multiplier. These 16 bits are multiplied and get and gives us the output of 32 bit. We can see that this is our 32 bit output of sine and this is our 32 bit output of cosine. Then these both outputs are getting towards the filter block. We can see that this is output of sine and cosine and we slice it from higher MSBs, higher most bits that are 31 down 16 that are the higher bits of our sine and cosine. Sine and cosine. So these 16 bits are connected with the FIR filter, that is a FIR sine wave and FIR cosine filter. So let us open the filter and see what's inside the filter. So these are the coefficients. How we get these coefficients we will discuss about that. First let me scroll down. You can see that this is our filter, this is our low pass filter. We can see that the pass band of filter is about 0 dBm and stop band is about 40 dBm and we get this value of 0.1 approximately. So whatever the frequency of whatever the input sampling frequency of this filter, we will multiply it with this 0.1. You can see that this is 0.02 megahertz, that is nearly equal to 20 kilohertz. So when we multiply the 20 kilohertz with 0.1, it will give you a 2 kilohertz cutoff. So this filter is designed for a 2 kilohertz cutoff frequency and input frequency of 5 megahertz. You don't have to change anything else and you will get the summary out here. This is our filter. One most important thing that you have to define your input data width and that is sine and you have to define your output data width, that I have defined 16, otherwise it will give you a 32 or 40 bits at output. That is not required for our project. So for now you have to design a filter. You must have a knowledge of signal processing for filter designing, but I would prefer you to learn about the filter designer application in So that's it for now. You can see that this is our sine filter with a frequency cutoff of 2 kilohertz, and this is our cosine filter with a frequency cutoff of about 2 kilo. No. Sorry, I am wrong. This cutoff is not about 2 kilohertz. We can see that this is 0 0.1, and whatever the sample frequency given here, we have to divide it by 2, because of Nyquist criteria. We have to this filter will work for 0 to 10 kilohertz only, because this if you notice this diagram, this is our normalized frequency, that is from 0 to 1. This thing 0 0.1, this is our cutoff frequency 0 0.1, that will be multiplied with 20 kilohertz divided by 2, that will give us 1 kilohertz cutoff. So these two filters are of 1 kilohertz cutoff frequency. Whatever the signal will be given towards this input, it will if the signal frequency is less than 1 kilohertz, then it will be given on the output, otherwise it will be attenuated. We can see in the simulation results later. So after that, we applied the magnitude formula, that is the squaring the x imaginary I and q component, that is I and q component, that is squared, and then it is summed, and then it will pass through the square root function. If we open the Cordic IP core, we can see that there are multiple functions here, rotate, translate, and we have chosen the square root. We have defined our input width and output width, and that's it. And we have to give the input, that is the sum of these I and q squared, and that is passed towards the output, and that will be calculated as magnitude output. So let us open the simulation. In the previous design which I have given to you, we have to give some signals, input and clock signal. We have to force clock signal or constant value to that signals in the simulation file, but in this project I have created a test bench file that will automatically assign the values to the variable. Let me tell you how. So the simulation file is now open. uh, Let me open the simulation test bench that I have created in Verilog. You can see that uh, this is our module, that is amplifier wrapper, that is known as amplifier wrapper, that is the block diagram. And you can see that there are several signals that are acting as an input and output. This is clock signal, valid signal, FIR cause, FIR sine, magnitude, phase input. These all are the input and output signals in the block diagram, which I have discussed in the start of video. So let me tell you that how this thing works. Now if you want that your input signal is of 2 kilohertz, then you have to assign a hexa value of 1a. How this 1a is calculated? As we know that for 2 kilohertz we get the decimal value of 26, that equates to the binary value of this. But if you see that there is a hexa value of 1a, so we write here as a 1a. Similarly, for 1 kilohertz frequency, we get the value of 13 by using the formula. So if we put 13 here, we can see that it is equates to value d. So we put here 000d, and its signal is of 16 bits. So we will define it by hexa value of 4. So similarly, for 5 kilohertz, 10 kilohertz, 1.5, or any other frequency, you can select the input value for this phase input signal. Okay, so for now our phase input signal is of 2 kilohertz, and our reference signal is of 1 kilohertz. So this is the test bench which I have written in VHDL. So let us open the file. Now we don't have to give the force signal towards these signals. So let me arrange the signals. So selecting the signal, reference signal, input, product, FIR cause, FIR sine, and magnitude out, and setting the radix to sine decimal, and waveform style to analog. Now starting the simulation and pressing this icon, and waiting for some time, we will get the simulation output. As you can see that simulation is running for some time, and this is our the reference signal, that is 1 kilohertz, and this is our input signal, that is 2 kilohertz. You can see that uh, for the time period for which a waveform of reference signal completed, there's two waveform that are completed with that same time period for the input signal. This is our 2 kilohertz signal, and this is our 1 kilohertz signal. This is the product of these two signal. Then this product is passed through the FIR filters, and we can see that after multiplying we have two components. 1 plus 2 is equal to 3 kilohertz, and 2 minus 1 is equal to 1 kilohertz. So the 3 kilohertz component will be filtered out from the filter, as we know that the cutoff for filter is about 1 kilohertz. So we are receiving the 1 kilohertz signal. You can see that this signal, the right one, the reference signal, and FIR, this signal, these signals are similar. So this signal is filtered out here, and then the magnitude is calculated at the last one. This is our magnitude that will that is the output of our squaring plus addition of I and Q signal, and then passing through the under root, and it will gives us a magnitude value. When you change the frequency of this input signal, you will notice that all these waveform will be changed. So for test purpose, we will pass this value. We see that for 2 kilohertz we have this value, and for if we give the input of 1.5 kilohertz, that approximate to decimal value of 20. Let's go for some higher frequency, so we will notice the change in frequency. We will give the input signal to the decimal value 65, and we will notice that the simulation will uh, this waveform will be changed. This is our input signal, and let's stop the simulation, and this is our phase input. We'll get radix on decimal. You can see that 26 is applied. This is 26 for 2 kilohertz. Now we are giving it 5 kilohertz, so we will apply 65. So now you can notice that the frequency of this input signal right here, this is now shifted from 2 kilohertz to 5 kilohertz. So let me stop the recording for some time. Now you can notice that the input frequency is changed from 2 kilohertz to 5 kilohertz. So by changing the values, I am stopping the simulation. So by changing these values, you can play with the frequency of your desired value, that is 5 kilohertz, 10 kilohertz, 1.5 kilohertz, or whatever you want to. But keep in mind that the cutoff frequency of the filter designed is 1 kilohertz. So you have to choose the frequency carefully for input signal and reference signal, such that their product will lies within the range of the cutoff frequency. For example, we can see that this is our 1 kilohertz and this is our 2 kilohertz. Whenever we multiply two frequencies, we will get whenever we multiply two signals in time domain, we will get the frequency added up and subtracted from each other. So we will get 2 minus 1 is equal to 1 kilohertz. One component is at 1 kilohertz, and 2 plus 1 is equal to 3 kilohertz, and another component is at 3 kilohertz. And when you apply the filter, we see that the 1 kilohertz component will be filtered here, and the 3 kilohertz component will be attenuated. Let me demonstrate you via pen. So uh, this is our input signal. I will write it as input, and the frequency of input signal is our 2 kilohertz. Okay, so and this is our reference signal, and the frequency of reference signal is 1 kilohertz. So when these signals are multiplied in time domain, their frequency component, let me draw the frequency. This is our 0 hertz DC component, and this is our T, and sorry, this is our F frequency. So initially we have 1 kilohertz, 1k, and 2k. When we multiply these signals, we will get two components, that is 2 plus 1 and 2 minus 1. So one component will be at 1k and another component will be at 3k. As you know that our filter is designed for 1 kilohertz, and after 1 kilohertz these frequencies are attenuated. So whatever the frequency of input signal after 1 kilohertz, that signal will be attenuated. So when this product is applied to the FIR filter response will be like that. So this component will be at the output and this component will be attenuated. So we can see that this signal and this signal, when we multiply it, this is our product, this component is attenuated and only this component is retained. This is our working procedure. So similarly you have to choose the frequency very carefully, such that the one component must be within this range of 1 kilohertz. So this is what I can do for you. This is more than what I have done for you, but as a student, I am also a student, so I have defined it very clearly. So I think it will clear all your doubts. So for now, you have to work yourself. Afterward, you have to work yourself and understand how this works. And this is the final statement from my side. Thank you so much.